In section 10.5, we look at yet another way to solve quadratic equations, and this is through a little bit of a complicated and yet really nifty method called completing the square. So first of all, think about when we had a quadratic which was a perfect square. This works out really nicely because we can factor this into x plus 4 squared, and because that's already set equal to 0, we can simply take the square root of each side and get x plus 4 equals 0, and we get our solution relatively quickly. What if we had something that was a little bit similar? So we have our x squared, we have our 8x, but instead of adding 16, we're now subtracting 9. So this one is not a perfect square. Now in this particular case, you could actually factor this pretty easily, but for illustration purposes, we want to go ahead and show how to complete the square. So first of all, we'll start by moving that constant to the other side of the equation. We want the x squared and the x terms by themselves, and then any constant moved over to the other side of the equal sign. So here's another example where we don't necessarily want everything set equal to 0. So in this case, we're going to add 9 to each side. We end up with x squared plus 8x equals 9. Next, take half of b, so in this case half of 8, and then square it. So we have half times 8 is 4, 4 squared is 16. That's the number that we really want here. That's what we want c to be. And we're going to force it to be c by adding that result to each side of our equation. So we had x squared plus 8x, now we have x squared plus 8x plus 16. We can do that as long as we also add 16 to the right hand side, and now we have 25. Now we factor that because we already know this is a perfect square. We set it up to be a perfect square, so we factor that as x plus 4 squared, and then the right hand side we still have 25. Now take the square root of each side. So we have x plus 4, and then remember that when we take the square root of 25, we need both the positive and the negative square root. So we have plus or minus 5. And then we solve that equation, subtract 4 from each side, but we need to subtract 4 both from a positive 5 and from a negative 5, so that we're going to get two roots here. So if we take negative 5 minus 4, we'll get negative 9. Positive 5 minus 4 will give us 1. So we have two solutions, negative 9 and 1, that will both satisfy this equation. Now another place that you can see an application of the idea of perfect squares is in a form of quadratic functions known as vertex form. So vertex form looks something like this. Y equals that leading coefficient a times x minus some constant in parentheses squared plus some constant. Now notice there's a subtraction already built into the formula, just like we had with point slope form, so that when h is positive, you'll actually see a subtraction inside the parentheses. Unlike that constant k here, if that's negative, then you'll see a subtraction there. If it's positive, you'll see addition. So remember, inside the parentheses, the sign is actually the opposite of what it initially appears to be. Outside the parentheses, the sign is exactly what it initially appears to be. So in this case, when we have y equals 2 times x minus 1 squared minus 5, we could set up a table of values, or we could notice that this is in vertex form, and we know that our vertex has an x-coordinate of 1, remember not negative 1, but 1, and our y-coordinate is negative 5. Okay, so the subtraction built in means x is a positive 1. In the case of the constant, it's not built in, so the subtraction means we have a negative 5. So the vertex is at 1, negative 5, and then our parabola will have the same shape as y equals, and now we look at that coefficient 2, so this will have the same shape as y equals 2x squared. So with our vertex at 1, negative 5, same shape means that when we move 1 to the right, we'll go up 2, and 1 to the left, we would also go up 2. One more to the right, we need to go up 6, or one more to the left, we go up 6. So we have that symmetry there. And so this is a relatively narrow parabola because of that coefficient being greater than 1. So we get something like this. Alright, and there you go. It's a quick way to graph a parabola if it's in that form. Okay, let's look at some examples. Solve each equation by completing the square and give exact answers. That means we could have some radicals or possibly some fractions involved. So first of all, we want x squared and x by itself, so we're going to subtract 45 from each side. And we end up with x squared plus 18x is equal to negative 45. Then we look at what we want to have as our constant on the left-hand side of the equal sign. So we take half of 18, so half of 18, and then we're going to square that. So half of 18 is 9, so we square 9 to get 81. That means we're going to add 81 to each side of our equation. So add 81, and we get x squared plus 18x plus 81 is equal to 36. Negative 45 plus 81 will give us 36. Now we can factor. We already know this is a perfect square. We set it up to be a perfect square. So this is x plus 9 squared equals 36. Then take the square root of each side. And remember that we need plus or minus the square root of 36. Oops, getting a little messy there. So we have on the left-hand side x plus 9, and on the right-hand side plus or minus 36. Plus or minus 6, sorry. We take the square root of 36 to get 6. Let me erase that just to make it a little more clear. Try that again. Plus or minus 6. So then we're going to subtract 9 from each side, so we get x equals, we could take a positive 6 minus 9 and a negative 6 minus 9. So x is equal to negative 3 or negative 15. So two solutions. Okay, number 2. Y squared plus 6y minus 38 equals 0. So we'll add 38 to each side. And we get y squared plus 6y equals 38. Then we take half of 6. So 1/2 times 6, and we're going to square it. So 1/2 times 6 is 3. We'll square that to get 9. So now we're going to add 9 to each side. So add 9, add 9. So we get y squared plus 6y plus 9 equals 47. Factor this out to y plus 3 squared equals 47, and then take the square root of each side. So y plus 3 equals plus or minus the square root of 47. Now notice 47 isn't a perfect square. As a matter of fact, we can't even factor anything out of that. So it's already in simplest radical form. But notice the directions again said give exact answers, so we're not going to turn this into a decimal. So, we do need to subtract 3 from each side though. And what we end up with then is, I'll move it up here, y is equal to plus or minus the square root of 47 minus 3. Or another way to write this is y equals, and we can switch the order as long as we keep the sign together. So negative 3 plus or minus the square root of 47, and sometimes you'll see this written separately. So it could be written like this, or sometimes you'll see it written as negative 3 plus the square root of 47, negative 3 minus the square root of 47. And for simplest radical form, or rather for giving an exact answer, we're done. Hey, number 3, 2v squared plus 16v minus 135 equals negative 9. So we're going to start by adding 135 to each side. Okay, and now we have 2v squared plus 16v equals 126. And now notice we could factor out a 2 here. So I'm going to go ahead and do that and say that 2v squared plus 8v is equal to 126, or in other words, we can divide by 2. So the 2's cancel, and we get v squared plus 8v equals 63. Now we take half of 8, so half times 8, and then we're going to square that. So 1/2 of 8 is 4. We square that and we get 16. So we're going to add 16 to each side now. So add 16, add 16. And we get v squared plus 8v plus 16 is equal to 79. So now I'm going to rewrite this. So we'll move it up here. We know that this is v plus 4 quantity squared is equal to 79. Take the square root of each side, so we get v plus 4 equals plus or minus the square root of 79, and then subtract 4 from each side. That's a 4, not a 9. And so we get v equals, and I'm going to go ahead and put the negative 4 in front, and then we have plus the square root of 79, or negative 4 minus the square root of 79. And again, 79 is not a perfect square, so we just leave it like that. Okay, finally, number 4, we have g squared minus 19g minus 29 equals negative 7g. So a couple of steps. First of all, we want all the g's to one side, so I'm going to add 7g, and at the same time, we want to move that constant over to the other side, so I'm going to add 29. So on the left-hand side, we have g squared. Negative 19 plus 7g is negative 12g. And of course, negative 29 plus 29 is 0. Then we have a negative 7g plus 7g. They cancel each other out. And we have a positive 29. So now we look at half of 12. And notice it doesn't really matter that it's a negative 12 because we're going to end up squaring it anyway. So we take half of negative 12 and square that. So this is equal to negative 6 in parentheses squared, which is a positive 36. That's what we want to add to each side. So plus 36 plus 36. So we get g squared minus 12g plus 36 is equal to 65. And now we know that we can factor this into g minus 6 squared, minus because the b is negative, equals 65. Take the square root of each side. G minus 6 is equal to the square root of 65, and then add 6 to each side. And again, I'm going to write that constant 6 out front. So g equals 6, and then, sorry, we need a plus or minus the square root of 65. So 6 plus the square root of 65, or 6 minus the square root of 65. Alright, so again, this is a little bit complicated at first, but if you do this plenty of times, you'll get the hang of it. So work hard and enjoy. Good luck.